General Motors is recalling nearly 600,000 vehicles due to a risk of engine failure.
A truck with 11,000 miles on the odometer should never die on a highway on-ramp. But that is exactly what has been happening, again and again, to owners who did everything right, and for years nobody inside the auto industry could agree on why. Picture the moment. A father merges onto the interstate with his family in the back seat, the engine humming the way it's supposed to, the payment on the truck barely 3 months old. Then there's a faint metallic tick, easy to mistake for a stone in the wheel well. 30 seconds later the tick becomes a knock, the knock becomes a shudder, and the engine locks up mid-merge, the power steering gone stiff, the brake pedal suddenly hard as concrete. He coasts to the shoulder on momentum alone, hazards blinking, semis roaring past close enough to rock the cab. This is not a rare anecdote. It is a pattern that repeated itself across hundreds of thousands of vehicles, from half-ton pickups to luxury SUVs, and for a long time, it had no clear name. For nearly 2 decades, automakers pursued a singular obsession: squeeze more power and more fuel economy out of smaller engines. Turbocharged 4- and 6-cylinder units began replacing the lazy, oversized V8s of the past. Federal fuel economy standards tightened year after year, and engineers responded the only way they could, by shrinking displacement while cranking up boost pressure, and by machining internal components to tolerances so fine they are measured in microns, a unit smaller than a human hair. It looked, on paper, like a triumph of engineering. More horsepower per liter than ever before, better fuel economy than the industry had promised just a decade earlier, and emissions numbers regulators were happy to sign off on. But something else was happening quietly, underneath the marketing copy and the showroom brochures, something nobody wanted to say out loud until the tow trucks started lining up. By the early 2020s, complaints were pouring into the National Highway Traffic Safety Administration describing an eerily consistent failure. Bearing knock. A ticking sound on cold starts. The faint smell of burnt oil drifting through the cabin vents. And then, often within days, sometimes within hours, total engine seizure. General Motors' 6.2-liter L87 V8, found in the Chevrolet Silverado and Tahoe, the GMC Sierra and Yukon, and the Cadillac Escalade, became the center of the storm. By April of 2025, GM had recalled nearly 600,000 vehicles built between 2021 and 2024, after federal regulators tied the failures to manufacturing defects inside the engine itself. And this was not a slow-motion, warning light kind of failure. Many of the trucks involved had fewer than 30,000 miles on them. Some had fewer than 5,000. These were engines owned by people who had changed their oil on schedule, followed the manual to the letter, and watched their engines die anyway. What made engineers finally sit up and take the problem seriously was not just the scale of the recall. It was the fact that GM was not alone. Toyota issued a recall covering roughly 127,000 Tundra pickups and Lexus LX 600 SUVs equipped with a V35A twin-turbo V6, citing the exact same failure mode, a bearing knock that escalated into total seizure. Honda faced complaints of V6 engines spinning bearings in vehicles with under 60,000 miles. Hyundai and Kia, already carrying the scars of a previous decade of engine recalls, found themselves back in the same position across a combined fleet of roughly 3 million vehicles. Different companies, different factories, different continents, different engineers who had never shared so much as a supplier contract, and yet they were all converging on an identical mechanical failure within roughly the same span of years. When rival engineering teams who guard their processes like state secrets all break in the exact same way at the exact same time, that is not coincidence. That is a shared cause hiding somewhere underneath all of them. So where was it hiding? The answer, according to investigators who tore these engines apart piece by piece, was small enough to get lost in the palm of a hand. Modern engine bearings do not touch the crankshaft directly. Instead, the crankshaft rides on a microscopically thin wedge of pressurized oil, a cushion so precise it is measured in fractions of the width of a human hair. That oil film is the only thing standing between two pieces of hardened steel spinning past each other thousands of times a minute. Introduce a single hard particle into that film, something as small as a stray metal shaving left behind during machining, and the cushion collapses. Metal meets metal. The bearing scores, then galls, then welds itself to the crankshaft journal, and the connecting rod tears free from the bottom. From the driver's seat, that sounds like a knock, then a hammer, then silence. Inside the engine block, it is closer to a small explosion, one the engine rarely survives. This is the cruel irony sitting at the center of the entire crisis. The very precision that makes a modern engine efficient is the same precision that makes it fragile. A 1990s small block V8 had bearing clearances roughly twice as generous as today's engines. A stray shaving of metal could tumble through that older design and get harmlessly caught in an oil filter without ever touching a bearing surface. Today's engines have no such margin. Industry analyses have long pointed to particulate contamination as the single largest driver of premature mechanical wear, responsible for a significant majority of early engine deaths industry-wide. Not bad design. Not driver abuse. Not extreme heat. Debris. Dirt. Microscopic shavings of steel that should never have made it past the factory floor in the first place. Understanding how that debris gets in requires stepping away from the dealership and onto the machining line where these engines are actually born. Crankshafts and connecting rods start life as raw forged steel, and machining that steel into its final shape inevitably throws off tiny metal shavings. In a properly run plant, every one of those shavings gets blown out, washed off, and inspected out of every oil passage before the engine is ever bolted together. But run a production line fast enough to build a modern engine plant's annual volume, often well into the hundreds of thousands of units, and perfection becomes nearly impossible to guarantee on every single unit. Some oil galleries get missed. Some shavings cling to a surface behind a thin film of residual oil, invisible to the naked eye, patiently waiting for the engine's very first startup to begin circulating. When GM traced its L87 failures back to their source, investigators found the trail led to a supplier machining crankshafts and connecting rods during specific production windows across 2023 and into early 2024. Microscopic debris had survived the cleaning process and settled inside the oil galleries, the internal channels that feed pressurized oil directly to the bearings. The very first time those engines fired, that debris began circulating, scoring bearing surfaces and journals with each rotation until a rod bearing eventually seized entirely. Toyota's engineers, working independently on an entirely different engine family on a different continent, arrived at strikingly similar conclusions. Machining debris and out-of-specification surface finishes on internal components built across a similar window between 2022 and 2024. Perhaps the most unsettling part of this entire story is that the fix did not immediately end it. Even after GM rolled out an official remedy, involving an oil flush and a switch to a higher viscosity lubricant meant to better cushion already stressed bearings, federal regulators logged dozens of new failure complaints from owners whose vehicles had already received the fix. Some of those owners had been given entirely new replacement engines under warranty. Those engines failed too. That detail alone prompted regulators to open a fresh investigation in early 2026 to determine whether the original remedy was actually solving the underlying problem, or simply delaying it. It is worth being honest about what a thicker oil can and cannot do. It can cushion a bearing that has already suffered mild wear, buying additional time before failure. What it cannot do is undo scoring that has already happened, and it cannot reach deep into an oil gallery and physically flush out debris still lodged inside. If contamination remains trapped somewhere in the system, no oil change on Earth guarantees it will not resurface on the next cold start. To their credit, automakers did not simply issue recalls and move on. In the aftermath of the worst failures, GM implemented a series of manufacturing changes aimed directly at the machining process behind the L87, adding more aggressive cleaning protocols, additional flushing stages designed specifically to dislodge debris from oil galleries, and new visual and ultrasonic inspection steps meant to catch contamination before an engine is ever sealed shut. Toyota tightened its own inspection processes for the V35A, adding surface finish checks on bearing journals. Honda and the Hyundai-Kia alliance leaned into automated optical inspection systems, essentially high-resolution cameras paired with computer vision, scanning every machined surface for irregularities far too small for a technician's eye to catch during a routine shift. Some manufacturing plants have gone even further, sealing off engine assembly lines from the rest of the factory floor entirely, upgrading air filtration systems to strip stray particles from the air before they ever settle on a part, and requiring workers to wear lint-free clothing while every tool on the line gets tracked and accounted for so that nothing gets left behind inside a running engine. It is a striking image when you stop to think about it. A pickup truck engine, built to survive mud, heat, towing, and decades of abuse, now being assembled in conditions that borrow directly from semiconductor manufacturing, the kind of clean room typically reserved for building computer chips. That comparison is not incidental. It is the entire point. An engine built to surgical tolerances now genuinely requires something close to surgical assembly conditions to survive its own design. There is also a quieter admission buried inside all of this. Some manufacturers have begun walking back their aggressive push toward ultra-thin oils like 0W20, recommending slightly heavier viscosities until inspection processes can confirm internal cleanliness. That is a tacit acknowledgement that the industry's relentless chase for marginal fuel economy gains may have pushed manufacturing tolerances further than factories could reliably deliver clean, at scale, every single time. None of this, though, changes the reality facing the millions of vehicles already on the road today, built during those specific problem windows, still carrying whatever debris may or may not be lodged inside their oil galleries. The manufacturing fixes rolling out now protect engines being built this year. They do nothing retroactively for the truck already sitting in someone's driveway with 100,000 miles left on its expected lifespan. Sensor technology that could theoretically catch this kind of failure early, real-time oil quality monitors, debris detection sensors, bearing temperature probes capable of sensing the first hint of scoring, exists in laboratories and prototype vehicles, but remains far from affordable enough to install across an entire mainstream lineup. So for now, the older, potentially affected vehicles continue rolling down the highway every single day, carrying an invisible variable nobody can fully account for. What this story ultimately reveals is not a single company cutting corners or a single factory falling asleep at the wheel. It is an entire industry caught between two forces pulling in opposite directions with increasing force every year. On one side, regulatory pressure demanding ever-improving fuel efficiency and lower emissions. On the other, generations of customers who grew up expecting 200,000 miles of reliable service from a vehicle, the way older, simpler, more forgiving engines used to deliver, almost as a matter of course. Squeezing those two expectations together has produced genuinely remarkable engineering, more horsepower and better mileage than anyone could have predicted 20 years ago, but it has also produced a margin for error that has nearly vanished entirely. The lesson emerging from all of this, expensively and very publicly, is a simple one. A machine engineered to surgical precision has to be built inside genuinely surgical conditions, and anything less turns that same precision, the very quality that makes a modern engine remarkable, into the quality that makes it fragile. Factories are adapting. Inspection systems are getting sharper. Automated cameras are replacing tired human eyes on the assembly line. But the fundamental tension between efficiency and durability has not disappeared, and it is not going away anytime soon, because the regulations pushing for smaller, tighter engines are not being rolled back, and the demand for durable, dependable vehicles is not fading either. Consider, too, what this failure actually feels like from behind the wheel, because engine seizure is not like most of the mechanical failures drivers have spent a lifetime learning to recognize. A flat tire announces itself with a thump and a pull, and there is time to ease off the gas and find the shoulder. A dead battery strands a car in a parking lot, not on an open highway at 70 miles an hour. Even a failing transmission tends to slip and hesitate for weeks before it finally gives out completely. Sudden bearing seizure offers almost none of that. There is no gradual decline, no dashboard warning that builds over days, no slow limp toward the nearest exit. One moment a driver is in full control of 2 tons of moving steel, and the next moment the power steering assist is gone, the brake booster has lost its vacuum, and the wheel feels like it has been set in concrete. That is precisely why regulators treat this as more than a routine warranty issue. It becomes a genuine highway safety question, because these failures tend to happen under load, while towing, while merging, while climbing a mountain grade, exactly the moments when an engine is working hardest and a driver has the least room to recover from a sudden loss of power. It is also worth pausing on just how strange the manufacturing detective work actually was. When engineers first cut open failed engines, they were not looking for a cracked casting or an obviously snapped component, the kind of failure that points straight back to a flawed drawing on an engineer's desk. Instead, they found scoring, thin spiral scratches along bearing surfaces that only a hard particle dragged through a pressurized oil film can produce. Oil samples pulled from the dead engines and examined under magnification revealed fine metallic grit, chemically matching the alloy of the engine's own internal components. In effect, some of these engines had been slowly sanding themselves apart from the inside, using shavings of their own steel as the abrasive. From there it became a genuine investigation, tracing failed units backward through supplier records, narrowing down which machining lines, which production shifts, and which cleaning stages had allowed contamination to slip through, until a specific window of build dates stood out clearly from the rest. The financial and logistical fallout has been just as significant as the mechanical story itself. A full engine replacement on an affected L87 equipped truck can require close to 18 hours of labor, more than 2 full working days at a dealership that also has to keep handling routine oil changes, brake jobs, and everything else that keeps the service department running. Multiply that labor burden across hundreds of thousands of vehicles, and it becomes clear why owners across the country reported wait times measured in weeks, sometimes months, rather than days. Loaner vehicles ran out. Service bays filled up. Fleet operators, the construction companies and contractors who depend on these trucks as daily working tools rather than personal vehicles, found themselves watching trucks pulled off job sites mid-contract, crews standing idle while equipment sat dead in a service queue nobody could speed up. None of this unfolded overnight, and it did not stem from any single bad decision made in any single boardroom. It built up gradually, one slightly tighter tolerance and one slightly thinner oil specification at a time, across roughly a decade of incremental engineering choices that each looked reasonable in isolation. It was only when those choices accumulated across an entire industry, tested simultaneously by rising production volumes and increasingly demanding efficiency targets, that the cracks finally became impossible to ignore. So if there is a truck or an SUV sitting in a driveway right now, built in one of those recall windows, running quietly and normally with no warning signs at all, this story is worth remembering the next time that engine turns over on a cold morning. The knock, if it ever comes, may start as something small enough to dismiss, a sound easy enough to blame on a loose heat shield or a stone caught somewhere underneath. But now there is a reason to listen a little more closely, and to understand that behind that faint tick may be something smaller than a grain of sand, quietly deciding how much longer that engine has left to run. There is something almost humbling in that. For all the computing power packed into a modern vehicle, the sensors, the software, the driver assistance systems monitoring a dozen variables at once, the difference between a truck that lasts 200,000 miles and one that dies in a driveway can still come down to a fleck of metal too small to see with the naked eye. Engineers now understand where that fleck comes from, how it travels, and what it does once it settles into a bearing. That understanding is real progress, and it is already reshaping how these engines get built. But understanding a problem and undoing its damage are two very different things, and for the families and fleet owners already living with an affected engine, the reassurance of a cleaner factory floor tomorrow offers little comfort about what might already be circulating quietly in their oil today. Maybe that is the real takeaway here, not a verdict on any single brand or any single engine, but a reminder of how much invisible trust gets built into something as ordinary as turning a key. Somewhere between the factory floor and the open road, that trust was tested in ways drivers never saw coming, and rebuilding it, one clean engine at a time, is going to take a lot longer than it took to lose.